Physics is a description of the universe. I could go on and on and on about this and say 1,000 things about it because I have that passion for physics. It's just built in. But I've distilled it down to this, and it turns out that everything that I have to say today is really based on this central idea. Human beings have a wonderful tendency to go out into the universe and look around and engage it with their natural curiosity. We want to find things out. Imagine early humans looking up into the sky and realizing that there are stars, and among the stars there are planets, that the sun rises and sets, that there are seasons. We make these observations, and we cannot help, as a species, to compulsively organize them so that we can understand the nature of our world. Inherent desire to understand what is this universe that we're living in. Well, since the earliest days of the human race until now, we've made that effort more and more sophisticated. And today, the issue of physics or the field of physics or the pursuit of physics has not changed. There are aspects of the universe that we're looking at quite curiously because we don't know why it behaves that way. And so we seek to describe it. I mentioned before, we're not looking for the truth because we've understood along the way that the truth is inaccessible to us. We're never going to get the truth from science alone. We're just seeking to describe the things that we do see. Physics is a description of the universe. But before I get to talking about some of the common aspects of physics that students study all the time, I'm going to take a little bit here at the beginning to just talk about science. I may have alluded in the introduction to the fact that I personally believe that human society as it exists today could do to be a bit more scientific. I claim that we lack scientific thinking. And in fact, I know for sure that there were other times in human history, for example, the Renaissance that you learn about in Western civilization, that there are other times in human history when we were more scientific. So I have some definitions here, lots of words. Science is, and I've come at it from I've essentially given it here two definitions. Science is a global human endeavor aimed at discovering how the universe works, both in the past and the future. It acts as a body of knowledge and a process of discovery. Lots of folks think about science in the context of the things that are known. And in particular, and in a very dangerous sense, this is what the scientists say. But science is not just a body of knowledge, it's also the process of discovering new things. And to that point, science is a systematic process involving observation, formulating questions, hypothesis testing, data analysis, and peer review. It is a very serious, formalized process. And it's important that it be that way because there is such a thing as good science and bad science. And very often, the citizens of our society, I don't know why I said civilian there, the citizens of our society can't tell the difference between what is good science and bad science. So science itself has to have a mechanism built in to keep things from going wrong that causes us to draw false conclusions about the way our universe actually works. So I talked about early human beings simply going out and observing the universe in terms of their senses, the things you can see and taste and smell and touch. Well, it doesn't take terribly long before you've gone out into the world and experienced most of what there is to experience. So in order to discover more about the universe, a good example of this would be, I think some of us are familiar with, there was an ancient idea that the world was composed of very few elements, that there was perhaps earth, water, fire, air, and that everything in the universe was composed of these things. Which is not a bad start as an idea, but today, all of you, having already taken a class in chemistry, know that this is an absurd idea, because the periodic table contains many more elements than simply 4. Well, in order to discover that, you need to be able to look closer at the universe than you can with your natural human senses. You need to be able to look closer. And to do that, we create measuring instruments. For example, to see things that are very small, we create microscopes. To see things that are very large, or I'm sorry, not large, but we see things that are very large, you just look at them like a mountain. To see things that are very far away, we invent telescopes. We invent tools that help us to observe the universe beyond our senses. We take our qualitative observations that are based on our senses, and through measurements that we make them quantitative. It's a little bit boring, and it definitely is a bother for students like yourselves. But if I take this meter stick, for example, instead of referring to a thing as far away, I can describe that observation with a number. Instead of saying a thing is far away, I can say it is 10 meters away. Instead of saying that I am very tall, which I am, I can say that I am 2 meters tall. I can take an observation of the senses and convert it into a number. And that is what our measuring devices do. And every measuring device that we create converts in some way an observation into a number. Whether it be this meter stick, which can convert an observation of space into centimeters, or a pan balance that you use in chemistry class to measure out a certain number of grams of a substance. Oh, this is heavier than this. Well, that may very well be true. But if I put those things on a pan balance, I now can describe that in the context of numbers. The reason why that's useful to me in science is because once I start converting my observations into numbers, making them quantitative as opposed to qualitative, I discover that there are patterns in the numbers. It's kind of a beautiful poetic thing to say about the universe, that the universe has patterns to it. The patterns are mathematical relationships. Anytime a person begins a physics class, they might have in the back of their mind a little bit of trepidation that there's going to be equations. Yeah, there's going to be equations, and since there's going to be equations, there's going to be math involved. But the reason is not because we're trying to ruin everybody's day, but instead the reason is that the patterns in the nature of the universe express themselves as mathematical relationships. And here's a fun bit of philosophy for you to ponder. Nobody knows why. Why does the universe organize itself mathematically? That is unknown. And I think it's possible that we'll never know why the universe is constructed mathematically. But the cool thing about mathematical relationships existing is that you can figure out unmeasurable things in the context of things that you can measure. As an example, I have this cartoon here where this fellow has a piece of cardstock, I guess, with a hole punched in it, and the hole is about 1 centimeter in diameter. Going outside and holding out that piece of cardstock, the sun shines on it, and like a pinhole camera, an image of the sun appears on the ground. This is fun to do during total eclipses, by the way, because you can create an image of the eclipse on the ground, because everyone knows, I think, we had an eclipse not too long ago. Everybody knows you shouldn't look at an eclipse because it's nearly as intense as the sun itself. You burn your retinas. So it creates an image on the ground. Well, there's a mathematical relationship that exists in this scenario. If I know the distance from the cardstock to the sun, which I do know, it's about 150 million kilometers, and your immediate question should be, well, how do you know that? Like, you got to get that number from somewhere. Yeah, we very cleverly figured out the distance to the sun. It's not easy, but we know. If we know that it's 150 million kilometers to the sun, and we know that we're holding the cardstock 110 centimeters above the ground, there's a relationship mathematically in the ratios of these distances. So if I write the diameter of the spot that appears on the ground, which I can measure, I get a ruler, I just measure that, it's right there on the ground, and the height of the cardstock, which I can measure with the same meter stick I just used. If I divide those numbers, that is, if I create that ratio, it's the same ratio as the diameter of the sun, which I don't know. And I can't go to the sun and put a meter stick up to it. That's not available to me. That's beyond my reach, so to speak. But I do know the distance to the sun, and using this and comparing the ratios, I can calculate the diameter of the sun remotely without actually having to go there, which really expands my human understanding of the way the world works. There's a great moment in a different physics course that I teach where I show my students that by measuring the time it takes the Earth to go around the sun, which is a year, of course, and the distance from the Earth to the sun, which now I know is 150 million kilometers. Just by having those measurements, I can calculate the mass of the sun, which is really an extraordinary achievement because I can't go to where the sun is. Well, how would you put the sun on a pan balance? How would you even determine the mass of the sun? And so you look in a book because someone has asked you some sort of clever science question. You look and you discover, we know the mass of the sun. How do we know? How do you know that? Because mathematical relationships exist in the universe, and I can use mathematical relationships to find things out, which is part of what science endeavors to do, to increase human knowledge and discover new things. Everyone has heard that there's a scientific method, but the truth is there's not one scientific method that everybody follows. If you go from textbook to textbook, you'll discover that there's not like exact agreement on what this method is. But each example of the method is close to sort of the same idea, and I'm going to give my own rendition of it in just a moment. But there are ideas about science that are dangerous, and I could list a few, but right now I choose to just do one. Science by attribution. Science does not work by a process whereby scientists who are very smart agree that a thing is true and therefore it's true. Science does not work that way. So anyone who starts a sentence with the phrase, scientists agree, is not making a scientific statement, because that is not at all how science works. That's called science by attribution, and the reason why I'm calling it out today is that there is actually an effort afoot out there in the world to shift away from the scientific method and toward science by attribution. You might wonder, why would you do that when science has gotten us this far just the way that it is? Well, it turns out that sometimes with science, there's an agenda. Folks who are trying to use science to make public policy or societal behavior change by misrepresentation of science. We're going to watch out for that. In general, the scientific method are principles and procedures for the systematic pursuit of knowledge involving the recognition, formulation of a problem, the collection of data through observation and experiment, and the formulation and testing of hypotheses. If you're going to be a scientist, you're going to follow this list of rules. And as I mentioned, I'm going to give us a set of these rules, a version that's good according to me. But as I say, it's not writ in stone how these steps go. But generally it goes like this. The first thing you need to do is figure out what you're curious about. You just sort of generally examine the world, or you read about the work of other scientists in different areas. Maybe you're interested in biology, chemistry, or physics, or any of the other scientific areas. And you say, there's a question that doesn't have an answer. There's a puzzle, some sort of strangeness of the universe. I would like to understand it so that I can describe it. So I have to figure out what the problem is that I want to solve. I don't just go into a laboratory, put on a white coat, and do science. It's pretty much obvious that you have to have something that you're trying to explain. So then you formulate a hypothesis, which is, to me, maybe the most important step of all. That is, you formulate an idea about what you suspect. Nice part about forming a hypothesis is your hypothesis doesn't need to be right. When you're making your guess, you don't have to go, gosh, I'm going to write a hypothesis. I hope I get it right. It doesn't work that way. We have kind of like a built-in instinct that we want to be right about things, but science doesn't work that way. I'm going to formulate a hypothesis, and the important thing about my hypothesis is not that it be right or wrong, but that it should be very easy to design an experiment based on the hypothesis to test it for its wrongness. I need to be able to design an experiment to check my hypothesis. Experimental design is tricky because you may be focusing on a particular individual problem, and all this other nonsense will get in the way of your experimentation and, so to speak, throw your results off. So experimental design is tricky in its own right and has its own set of very careful rules that we've discovered throughout history. And then you go into the laboratory and you collect all of your data. You don't collect the data trying to make sure that the data is right. You don't do it trying to make sure that the data is wrong. You're not trying to solve the question of your hypothesis right there in the moment. You just very honestly and methodically collect the data, and then we see where it lands. We're going to do whatever sort of math we need to do, and then when we're all done with that, we're going to decide if our data supports or refutes the hypothesis. That's more or less the scientific method, and it certainly suits me the way that I understand it. Now here at the bottom of the screen, you see this funny set of cards. Here's a story about the scientific method and how it works in the real world. There are folk who observe social interaction among human beings, and they think, you know what? That person there is psychic. That person is psychic. Psychic phenomenon. Shorthand, I guess, the ability of one individual person to read the thoughts of another person. You may say there are other forms. You could there are people who supposedly can move things with the power of their mind, telekinesis, that sort of thing. It's very exciting stuff. So a group of scientists, I'm sorry I don't have the exact reference on this. I think it was in the early 1970s, pretty sure. They decided to do an experiment, and what they did was, you're maybe psychic. So I sit you down, and I've got cards like the ones that are pictured on the screen here: circle, plus sign, wavy, square. And I hold up a card, and I look at it. I can see it, and you can't. And you think about what I'm thinking about, and you try to answer. And my hypothesis for this experiment is that if I show you the cards, you'll be able to read my mind and know what the cards are. So you take a guess, and you're right or you're wrong, and then I put it down, and we keep statistics on it, because obviously you could guess right accidentally or just by statistics. And same thing for guessing wrong. So we do it a lot with a lot of people. We do a whole big experiment. This was done at a university, by the way. So this was real science was being done in a laboratory with folk. And they discovered, based on their data, that the psychic phenomenon was real. The data supported the hypothesis. The subjects were psychic. Wow, that's incredible. They did science, and the folk turned out psychic. Yes, but if you do things just by chance, you get a certain distribution of results mathematically. And this result that they got was different from the typical statistics in a way that suggested that it was better than random guessing. Yeah. But then what happened in the subsequent years is that people began to question the experimental method. They said, I don't know, that experiment, you're just holding up cards. I got another experiment that we're going to do many years later, and I'm going to hold up the cards, and I'm going to attach electrodes to the people's heads, and I'm going to collect electrical data from their brains as they do it. And I'm going to do more people. I'm going to select the people according to a criterion and whatnot. And what that newer experiment that measured the phenomenon more precisely discovered was that, in fact, the folks weren't psychic. It was a flaw in the experiment. The reason why I bring up this story is to point out that doing the scientific method doesn't guarantee you the truth at the end, and that the scientific process is always evolving. We're always improving our science. Here's a critically important point. Although I'll never know for sure that my hypothesis is correct, one very important characteristic of any good hypothesis is that when I look closer at the phenomenon, the hypothesis becomes more correct, not less so. So the hypothesis can change over time, and the experiments can improve that can change the way we think about things. For example, I love this statement. During the plague, women who lived alone had much lower instances of the plague. This is because they were witches. That's a little bit silly, isn't it? In our modern understanding, we've left the idea of witches behind to a certain extent. I don't think completely, but mostly we leave the witches to Halloween costumes. But for a time, of course, that's what people believe. But that hypothesis can change and evolve, and when it does, you realize that there are factors in the experiment that need to be considered, because during the plague, when women who lived, during the plague, women who lived alone had much lower instances of the plague, and this is because they were likely to own cats, and the cats killed the rats that were carrying the disease. And that hypothesis better fits the experimental result. It's more precise, more detailed, and is ultimately better science. So science is a sophisticated process, but when you get down to it, it's easy to tell the difference between good science and poor science. A word that gets thrown around all the time, and I'm never going to win this battle, is fact. I want to say that there are no facts, that there is no observation or measurement or experimental result that is so well verified that I imagine that it will never ever be overturned. I just can't get behind that. So the word fact is a difficult one. We're going to have to ease up on what it means. I think in most of our minds, the word fact means absolutely immutably true. And that is not correct. It's a bit looser than that. While we can't actually know any facts, we can drive an idea or a measurement or observation very, very close to agreement among all scientists. And so a fact is a close agreement by competent observers, like credible scientists who make a series of observations about the same phenomena. So if I go into a lab and I do an experiment, chances are someone else is going to do the same experiment. And when we come to the same conclusion, and so do our other colleagues and so do our other colleagues, it's not going to bother us that there is some flat earther crackpot over there who says that we're wrong. Because we have a very agreeable consensus among competent scientists, and then we're content to call that a fact, but we should be very careful with the word. A hypothesis is an educated guess. It's only presumed to be correct. So there's an important difference there between those concepts, and that's what I want to focus on there. Also, not so much laws and principles, but theories. There's a little bit of difficulty here in how, in our everyday language, we handle these terms. A law or a principle, for example, I don't think anybody would be surprised to hear me say, the law of gravitation. That's a common statement. A law or a principle is a hypothesis that's been tested repeatedly and has not been contradicted. Ages ago, Isaac Newton figured out how gravity works, and since then, we've never been able to do experiments that contradict it. And so instead of calling it Newton's clever idea about gravity, we just start calling it the law of gravity, because it's so reliable that every experiment that we do agrees with that calculation. Does that mean that gravitation as described by Isaac Newton is true? It does not mean that, because it turns out our universe and the structure and evolution of the universe is a bit stranger than that. And so it's entirely possible that the law of gravity is not exactly right, and we're working on that today. That's an issue right now in physics. A theory is a synthesis of a large body of information that encompasses well-tested and verified hypotheses about certain aspects of the natural world. When I put this one in, what I'm thinking of most commonly is like something happens and someone looks at it for the very first time and says, I've got a theory. That's a misuse of the word theory. You don't look at a thing or encounter it for the first time and say, I have a theory. What you should say, but people don't say, is you encounter a phenomenon for the first time and say, I have a hypothesis about this. Anybody who said that in common society and not in a science classroom would sound a bit nerdy. I have a hypothesis about that. So you say, I have a theory. Sounds very official. But the fact of the matter is, a hypothesis doesn't become a theory until it's well tested, there's lots of experimental evidence testing its veracity, and it includes all other side aspects of that particular idea. That is what creates a theory. Science is not the same as technology. In a bit, I'm going to assert to you that we do not live in a scientific age. At which point you could come back at me and say, yeah, but look at all this technology that we have. Technology is not science. What happens is that science concerns itself with gathering and organizing knowledge. And once all of that information is uncovered, technology uses that scientific knowledge to practical purpose and gives us tools to further explore the universe. A really great example of this is when the electron was discovered. And from our studies in chemistry, we know that atoms are composed of what are called subatomic particles, the protons, the neutrons, and electrons. Minuscule particles of electric charge which participate in all of that stuff that becomes chemistry. When the electron was discovered, there was no practical purpose for it whatsoever. And some folk at the time said it out loud. What a useless discovery, the electron. Purposeless, pointless. Why did you even go through the effort to do that? And yet today, the vast majority of our modern technology is based on the understanding of the behavior of electrons. Your cell phone does not function and cannot be created or conceived without understanding the nature of electrons. Science gives us the knowledge and the understanding, and technology applies that knowledge and understanding to the creation of products which then advance human civilization.